Hello, we've got one section to cover during this video, and it's 7.6 about exponential, logarithmic, and quadratic functions. The exponential and logarithmic really go together, and the quadratic is kind of its own thing. First of all, an exponential function. An exponential function, well, is going to have an exponent in it, but the exponent is where your variable is. So what is being raised to a power is not a variable, it's a whole number. I know it looks kind of like a variable here where we have a b, but this b, if you look, is a positive constant, so just a positive number, and it can't be 1. The reason it can't be 1 is because then we would just have a straight line. 1 raised to the 1 is 1, 1 raised to the second is 1, 1 raised to the third is 1. The value would never change. So it's a positive number, and it does not equal 1. And then x, it says x is any real number. This is the formal definition of an exponential function, but that exponent is where you're going to find your variable. This happens when our rate of change is actually changing, and that's really very common. A lot of times, you start off slow and then you speed up. That could even refer to, you traveling somewhere. So what is happening here is that we have a curve that is really not very steep, and then suddenly it gets extremely steep. One place that this could apply might be somewhat modeled by understanding mathematics. You're going along and you don't get it, you don't get it, you don't get it, you don't get it, and then suddenly you do get it. And the more you get, the more you're able to understand after that. So the more you go, the more you start to increase. And so that's where I have, sometimes I'm going to say the more, and that's just saying that the more you go to the right, the more the change is happening. It's just one curve though, and it heads up. So let's look at that, because we can graph these. There's several methods to graphing, but we're just going to kind of stick with, we can make a table of values and plot points. Now I am going to say that as you put in some numbers, sometimes on these, because of those little bitty values that are over here to the left, you have tiny little decimals. So you're not going to be able to graph those very precisely, but you're going to have to get enough values that you can make a graph. So if some of them are not things you can graph, that's okay, because when you're doing your online homework, you don't have to plot 15 points. You have to get a curve on there and tell it a couple of points to go through, or identify the correct graph. What we're going to do is take these values and then just plug them in for x. So if I plug in -2, then I will get 3 to the, well, -2 minus 1 actually becomes -3. Now, you may or may not know this, but a negative exponent is the same as saying it should have been on the other side of the fraction bar. So this is 1/3 to the third. And what this is going to be is a tiny decimal, because 3 to the third is 27, so it's 1/27th. But just pick up your calculator, and even with that negative, you can go 3 raised to the -3. And it is approximately, because it's such a tiny little decimal there, so I'm trying to put a wavy equals, it is approximately 0.037. That is so small, so I can tell it's really going to be hugging that x-axis there. So f of -1 is going to be 3 to the -2. So that becomes 1/3 squared. 1/3 squared is 1/9, and that is approximately 0.111. So now when I put in a 0, I have -1, which is 1/3, which is approximately 0.333. F of 1. 1 minus 1 is 0, because we've got that -1 up there. Anything raised to the 0 power is 1. Hey, that's not a bad point. I like that one. F of 1 is 1. If I go over 1, I can go up 1, and I have a dot there to put. F of 2 3 to the 2 minus 1 is 3 to the first, which is 3. That's not a bad point. So if I go over 2, I can go up 3. You might see I'm doing that on the graph over there to the right. Okay, so those are pretty good points right there. 1, 1, and 2, 3. But I probably need to get another one kind of to establish a curve. 2 points gives us a straight line, but you really kind of need another point to get a curve. So I'm going to use this one at, when I was at 0, I was 1/3 of the way up and just kind of get that. And now what I'm going to try to do is draw a curve through there. And we know when I'm looking down at this little black pad with no lines on it and trying to draw, I'm probably going to miss the points. But it's not terrible. All of these are going to be shaped very similar. So if you see this shape back here, we've got all these points on it. It's going to be really close to the x-axis. It doesn't cross it. It stays above it there. That x-axis, kind of just visualize a dotted line. That's ground level. These don't go below ground level. They're always going to stay positive because we have a base, like where this 3 is. The base is positive, and when you raise a positive number to something, you get a positive, even though it can be really small. Okay, so we'll do one more of those. This one is 2 to the x, and it doesn't tell me what to plug in because you don't always have to plug in all of those numbers. What I'm going to do is just kind of make a table. And I'm just going to do an x, and then what does that equal? So I'm going to plug in a -1, a 0, and a 1. So it's just kind of showing that work differently. If I plug in a -1, 2 to the -1, and feel free to pick up a calculator and punch that in. 2 raised to the -1 is 1/2. 2 raised to the 0 for this one. Well, anything raised to the 0 is 1. And then 2 raised to the first power, 2 to the 1 is 2. So here I have 3 pretty decent points. I've got, now these are over here on this graph, it's counted by 2, so it's still pretty small. But I've got -1 and 1/2. I have 0 and 1. And then I have 1 and 2. So again, I'm going to try to hit those 3 points and try to stay above. I know it'll be a kind of shaky line and we'll have some issues there, but notice how I did try to stay above that x-axis. Okay, so those are exponential functions. As soon as we learn to do something, it seems like we start to turn it around. A logarithmic function is what turns it around. And a logarithmic function is a different way of writing it. You can still see it's kind of a similar curve, but instead of headed up with it not crossing the x-axis, this one doesn't cross the y-axis and it heads out more. So the more you go, the less steep it is. So this one might be illustrated where instead of your understanding, where your understanding is I don't understand, suddenly I do. This one might be the level of difficulty. It is extremely difficult, and then it's just getting a little more difficult as we go. One thing is to recognize that both of these have a base. And this page right here is the formal definition of a logarithmic function, but I think the most important thing you can take from this is probably the shape of this graph and the recognition that x, up here where x is, it starts off by saying x has to be greater than 0. B is also greater than 0. So if you see a number though where x is not greater than 0, that's a no solution. We are looking for numbers to be greater than 0 here. Let's see how we can do this. One of the things you want to do is just look at the relationship of where the numbers are. This is called the base. And this is the base. B is the base. They're in a different place. On a logarithmic, it's the little lower number. And then on the exponential, it's what's holding up that exponent. The y value, on the other hand, is the exponent. And you can see that very clearly in the exponential form. But the thing is, y is still the exponent because these are two forms of the same thing. But here's the kicker. If y is the exponent in the logarithmic form, and y is equal to log base b of x, then the truth of the matter is log base b of x is actually an exponent. It's just written in a totally crazy different way. But it allows us to do some more complicated math we're not dealing with right now. What you want to do is learn to rewrite. Take a function from one form and turn it into the other form. Now it says here on the tip, start at the base, move to the other side of the equation, and then back. Looking above in this blue box on the exponential form, if you started at the base b, then you would move to the other side of the equation and have x equals y. So it would be log base b of x equals y. Or here what we're going to do is we're going to start at the base, go to the other side, and then back. On this particular one, we would say 2 to the y equals x. Now, it doesn't matter that the y is the exponent right now. The idea is the rewrite, that you can rearrange from one form to the other. Okay, rearrange from one form to the other. I don't think I have another example on here, but let me just kind of put one down. Another example. If you had y equals 4 to the x plus 1. 4 is the base. So if we were going to do this one, we would start here at the base and say, okay, my base is 4. So then log base 4 of, now swing to the other side, of y is equal to not just x, but that entire parentheses, x plus 1. One of them has a y equal, and the other one didn't have a y equal. That's true up in our definition as well as in both of those examples, but you're focusing in on what the base is to rewrite that. Just like we can graph exponential functions, we can graph logarithmic functions. But if you need to graph and find particular points, notice in the blue box it says that y log base b of x reverses the x and y coordinates. So really, the easiest thing to do is just think of what the x, y coordinates would be for the related equation and then flip them all. So if I were going to take and graph y equals log base 3 of x, our brains are not programmed to think in logarithms. So what we're going to do is switch over to the related function, not the same, but the related one. It is related to the exponential function that has the same base. Now, I'm not rewriting this. That's different because I'm actually going to trade out my x and y. It's related to y equals 3 to the x. That's not a rewrite. I didn't do a loop-de-loop thing. I just said, okay, the base is 3. So I'm going to look at 3 to the x. So if I were doing 3 to the x, similar to what I did before, I could plug in an x and get out a y value. And I'm going to do it with these 3 points. They're just kind of my go-tos. 3 to the negative 1 is 1/3. 3 to the 0 is 1. And then 3 to the 1 is 3. So then I have those points. I am going to trade them and say, okay, if I go out 1/3, I'll be at negative 1. 1 will give me 0, and 3 will give me 1. These are the points then that I can graph to get my logarithm. And remember, the logarithm is going to kind of have that other shape that kind of does this sort of a thing. 1/3, which means barely over, and 1 down. Oh, I kind of put a line there, but we're going to let that go. 1 over, and 0 up or down. And then I need to go 3 over and 1 up or down. So again, you can see this is a real steep sort of thing at the beginning. And then that levels off somewhat. It's still going up, but not much. And it should not cross the y-axis. It's really close to it, but it's not crossing the y-axis. So that's our logarithm. You think of the related one, and then we turn it around. We're going to do another one of those. Same sort of thing. Because it reverses it, we're going to identify, first of all, what is our related function. The base is 2. So my exponential function with a base of 2 would be 2 to the x. Same base there, but -1, 0, and 1. 2 to the -1 is 1/2. 2 to the 0 is 1. And 2 to the 1 is 2. And by the way, if you were wanting to just graph this in general, when you plug in a -1, you get 1 over b. See that base there? That's how I did that so quickly. If you plug in a 0 for x, you get 1 every time. And then plug in a 1 and it gives you b. So there's a pattern I'm using there. That's what lets me do those points so quickly. Just kind of take that base of 2 and I flipped it over for 1/2. So if that one is my related function, then just like I did up here on this one, I want to trade all of those x and y values. So now I'm going to trade those points, and it's going to give me 1/2, -1, 1, 0, and 2, 1. And those are the points that I'm actually going to go plot over there for my logarithm. Half, that's tiny, -1. 1, 0, and then 2, 1. So see, it looks very much the same. It's not exactly the same, but it's awfully close. If you were trying to identify a graph, you're going to really need to enlarge that so that you can see values and maybe type something into your graphing calculator so you can make a comparison of that along the way. Now we're going to switch over and do a very different type of thing, because our other one we did exponential and logarithmic, and now we need to do quadratics. Before I do that though, I just want to mention a couple of applications. We've got one application problem at the end, but just to remind you, what sort of thing in real life would do like this? 2 to the x is very common for like bacterial growth or even cell growth. If you have a cell, it divides and then there's 2 of them. Then they both divide and you have 4. They all divide, and suddenly you have 8, 16. And it's doubling every single time it does that. 16, 32, 64, 128. That's exponential growth. That is a very common type of one that actually has a real application, and I think we've got one similar to that that has to do with population growth at the end. But on a quadratic is an equation that starts off with this particular form here, ax squared plus bx plus c. And when you graph those, they kind of look like a horseshoe shape. It's not really, it gets a little bit wider as it goes up, but maybe an umbrella sort of a shape then. So it could be a parabola, is what the name of the graph is, but it either opens up or it opens down. Okay, that's what the shape would look like. The vertex is that turning point. The x-intercept is where it crosses the x-axis. The y-intercept is where it crosses the y-axis. So these are the things that your instructions are going to tell you to do all the time. Does it open upward or downward? What's the vertex? Find the x-intercepts, find the y-intercepts, and graph the parabola. So this is a key slide then about information. You might want to take a picture of this or pause it and write this down. But to determine if the graph opens up or down, which is your first question, you're going to look at this very first number here, A. And if A is positive, then it opens up, because positive is, you know, that smiley face. And if A is negative, it opens down. So you just look at A, and if A, that's all you have to do to determine if it opens up or down. Then there's a little formula for finding the very beginning of the vertex. The vertex, we often call that point HK. But the thing is, to find the vertex, you're going to take the A and the B from your given equation up here and do the opposite of B over 2A. Once you get the opposite of B over 2A and you know what number it is, what this F of that means, you want to plug that in. So you'll take that answer, whatever that is, and you're going to take it back up here and plug it in for X to get your Y value. Now the X-intercepts occur when Y is equal to 0, so we have to let Y equal 0, and then we have to solve, which means you're probably going to factor, but you might use the quadratic formula. And then the Y-intercept occurs when X equals 0, and that's our favorite because it's so quick to just think, well, if X is 0, the only thing left in this equation is C. So if X is equal to 0, all that's left is C. So you can just look up there and tell what your answer is for that Y-intercept. And the Y-intercept is actually a point when X is 0, so that point is going to be 0, C. Now let's apply this. The next two are examples of this, and we're going to take this and work these out. First of all, if I need to know if it opens up or down, I need to look at A. Now A is not shown, but there's kind of an understood 1 right there, because if you have an x squared, then you have 1x squared. Since 1 is positive, this thing opens upward. Now to find the vertex, the very first thing you have to do is the opposite of B over 2A. And in this case, that is -4 because B is that second number. And then 2 times A, don't forget A is that understood 1. So that ends up being -2. So my first number from the vertex is -2. Now to find this second number, you have to take that -2 and plug it in for X. And you can use your calculator to help you, but I want to write it out here. So that's going to be -2 squared plus 4 times -2 minus 5. So simplifying that, that is 4 minus 8 minus 5. Now don't forget, if you're using a calculator, you have to put the parentheses around that negative, or you're going to end up getting a -4 there, and it'll be wrong. The parentheses are important. So 4 minus 8 is -4, minus 5 more is -9. That is the second value of my vertex. So like I could go ahead and plot that point, -2, -9. That's my vertex. Now the x-intercept occurs when this equals 0. So I'm going to put 0 equals x squared plus 4x minus 5. Now I'm going to factor this. What multiplies to 5 but subtracts to 4? And so that's going to be a +5 and a -1 here, where we combined it at, and then I've got an x in both of them. So now that's factored, which the x-intercepts then are where this whole thing has to equal 0. This only equals 0 if each of these parentheses equals 0. So if x plus 5 equals 0, then x is -5. And I have an intercept right there. So I'm going to go put that on 0, -5. So now that one's graphed. Now the other one said x minus 1, but if x minus 1 is equal to 0, then x would have to be 1. So now I have my other intercept. Now, you'll notice that those are both like 1.5 units on each side of the line that has this vertex in it. It always should be balanced there. Now the y-intercept is easier to find. The y-intercept happens when x is 0. And when x is 0, all the disappears except for that c value, so you get -5. So I have 0, -5. Now to graph the parabola, I wish I thought I were talented enough to connect this as a nice, beautiful, smooth curve here and hit all of those. But you know I'm going to miss it, okay? It should be a smooth curve, and I kind of started okay, but I sure messed that one up. I wish I had gotten it more rounded. But that's the idea of the curve, and at least when you're doing those, you know, on your online graphing, it does put that shape on there, but you have to identify 2 clear points for your online graphing. 2 clear points that you're going to need. Use the vertex, and then you can use another point. The next easiest one to find is your y-intercept. If you let x be 0, that y-intercept is a real easy one for you to find. Okay, so we've graphed it. Does it open upward or downward? This one, a is -1. Since a is -1, this one opens downward. The vertex, first thing you want to do is the opposite of b over 2a. In this case, that's going to be -2 over 2 times -1, which ends up being just a +1. So my vertex, the first number in my vertex is 1. To get the second number here, you need to plug a 1 in to all of those x values. So I get -1 squared. Now I didn't put parentheses this time because I don't need that negative squared. It's just the x I'm squaring. Plus 2 times 1 plus 3. So that is -1 plus 2 plus 3. -1 plus 2 is 1, and 1 plus 3 is 4. So my vertex happens at 1, 4. X-intercepts. Well, the x-intercepts happen when the whole thing equals 0. What you may not remember, you might, but you don't want to factor with a negative in front of your x squared. So what I'm going to do next is divide all of those numbers by -1. You can do that because I'm dividing on both sides of the equals. But 0 divided by -1 is still 0. But it gives me this handy little feature of getting rid of that negative at the lead that I didn't need. I can factor this, what multiplies to 3 but has a difference of 2. So I'm going to put difference of -2. So I'm going to need an x minus 3 and an x plus 1. Each of these parentheses, if they each equal 0 one at a time, that's how I get my intercept. So if x minus 3 is equal to 0, then x is equal to 3. So I now have an x-intercept of 3, 0. And if it's x plus 1 that equals 0, then x would need to equal -1 for that to be true. So x is -1. So I have those 3, but I also need the y-intercept. The y-intercept occurs when x is 0. So if you plug in a 0, and I'm writing this one differently this time. I'm just going to go ahead and put 0 for x. If x is 0 and you plug it in, then those ax squared plus bx disappear, and you're just left with the 3. So I have a y-intercept at 0, 3. Now, if I could graph it again, if I could connect this into a nice smooth curve, it would open down. We know that when I try to draw this, this is not going to work well. But the 2 points that would be easiest for you, probably when you're doing this online, is to use that vertex, because you're going to have to take the shape and put it on the graph, and then click the shape, and then it pops up these 2 little dots that you can move around, and put one of them at the vertex and one of them at your y-intercept. The only other type of graphing it's going to have you do would be possibly choosing the correct graph. So again, kind of sloppy here, but it's going to have to do with the sort of graphing tools that I have in here. Those are our concepts. We have exponential functions. Those are the ones that are going up and they don't cross the x-axis. Then we had our logarithmic functions. They don't cross the y-axis and they're going up but not as steep. The more you go, the less steep it is. Then we had our quadratic functions. And now, just for one example, there's no way I could work all of your examples, but sometimes you're just going to have word problems. And the bigger thing there is, I think, read through and try to determine what everything means. It says here that A is the world population, and it tells you to find the world population. So that's essentially telling you to find A. And this concept of since 1975, it doesn't say that on this screen, but generally when they do something like that, there will be something that tells you that T is the number of years since. And then it will give you whatever year they want. So sometimes, you know, since 1975, or T is the number of years since the year 2000. T is the number of years. So what you have to do is figure out how many years past 1975 you're talking about. Well, they've got 2014 for the year that you're wanting to work. So 2014 is not T. That would be a common mistake. But what you've got to do is do 2014 minus 1975. And that's 39. T is going to be 39 in our problem. So then you're going to take T and just plug in a 39. Now, E is a number. I don't know if you're familiar with it or not, but it's a number on your calculator. You have a key for it. It is approximately 2.72, but not exact, just like pi isn't exactly 3.14. So generally, you should use the key on your calculator. Depending on what your calculator is, it might be the second function of ln. So you might need to look on your calculator for an ln. If you have a basic calculator, it's written above this ln key, so I would have to hit the second and then ln to get that. I'm just going to type it in, though. 4 and then second ln. That opened up an e to the. It's got parentheses there, and it's ready for me to type that in. So now I'm going to put 0.019 times 39, close parentheses, enter. And what I get on my calculator is 8.392129993, and then my calculator quit showing me. But here's the thing, this is in billions. It says so right up at the beginning. So you're going to have to read the instructions carefully, and it's going to tell you what to round it to. But we're going to take this to 1 decimal, and we're going to say about 8.4. But then expect to have to choose the right label. So this is about 8.4 billion. Well, you can tell that that's outdated information. We've got a lot more people in the world than that today. But that was still the application. So the main thing I can tell you about the application problems is read very carefully, see what it's asking you to round to. If it does have an E, then you're looking for that key on your calculator. Don't forget to answer your discussion questions and email me if you have particular questions. Thanks, guys.